In traditional construction planning, the critical path method assumes that a schedule is deterministic. If you are building a massive steel bridge, the model requires a precise, fixed time estimate for every piece of the project. But large-scale engineering does not operate in a vacuum. Projects face systemic uncertainty, severe weather, supply chain disruptions, and human error. In a deterministic model, a single unexpected delay on a Tuesday creates a cascading geometric shift that pushes every subsequent task off its scheduled mark, ruining the entire timeline. To capture and map this real-world uncertainty, engineers and project managers utilize the program evaluation and review technique, commonly known as PERT. PERT abandons the illusion of absolute precision. Instead, it treats the duration of every project activity as a random variable, rather than a fixed guarantee. Over the next few minutes, we will track exactly how subjective time estimates are translated into objective, statistical probabilities of project completion. To truly control a complex project, an engineer must stop guessing at deadlines and start mathematically modeling risk. To understand the system, we first look at the architecture of a single, isolated task. This hand-drawn key shows the standard layout of a project node, divided into 6 distinct compartments. The central block, labeled A here, represents the actual duration. Under traditional methods, a manager would drop a single number into this box. PERT requires 3 separate inputs: an optimistic time, a most likely time, and a pessimistic time. The optimistic estimate assumes highly favorable conditions with 0 friction. The pessimistic estimate anticipates highly unfavorable conditions where every negative risk occurs. Together, they establish the extreme boundaries of the task. Within these bounds, activity durations typically follow a skewed beta distribution. This skew exists because delays tend to compound quickly when a task falls behind, but early finishes rarely accelerate the work by the same margin. The most likely estimate reflects the standard expected conditions, and it is plotted directly beneath the peak of this skewed curve. To find the expected time for this task, PERT uses a weighted average formula. We add the optimistic time, 4 times the most likely time, and the pessimistic time, then divide by 6. Giving a weight of 4 to the most likely outcome pulls the expected time closer to the statistical center of gravity. We also calculate the variance of the task, subtracting the optimistic time from the pessimistic time, dividing by 6, and squaring the result. This range represents a complete 6 sigma spread of possibility. At the activity level, PERT turns every single task from a static guess into a quantifiable probability curve. When we zoom out, we see this network diagram mapping how these probabilistic nodes link together to form an entire interdependent project. To calculate the total duration of the project, we must track time through the network using 2 distinct mathematical passes. First, we look at the top row of the node, which houses the earliest start and earliest finish times. By executing a forward pass from the start node to the end node, we add the expected durations together to calculate the absolute earliest a project can finish. Then we look at the bottom row, which tracks the latest start and latest finish times. This completed diagram illustrates the backward pass. Starting from the final project deadline on the far right, we subtract durations moving left, finding the absolute latest each task can start without causing a delay. The interaction between these 2 passes generates a metric known as total float, or slack. We define slack mathematically by subtracting the earliest start time from the latest start time. In practice, slack represents the exact amount of time an activity can sit idle before it forces the entire project off schedule. By calculating the slack for every node, engineers map out the hidden flexibilities and the absolute rigidities within a massive network. Notice on this specific chart how certain nodes have a bottom-middle slack value highlighted in red, reading exactly 0. A continuous sequence of these 0 slack nodes forms the critical path. Looking at this diagram, thick red arrows cut through the surrounding noise to trace the primary sequence, tasks A to B to H to I, and finally J. The total length of this specific path dictates the absolute minimum time required to complete the construction. Because there is 0 slack here, any delay on a critical path node results in an immediate 1-to-1 delay for the entire project system. Management must look past the distraction of non-critical tasks and direct their risk mitigation straight at this 0 slack spine. Remember that every individual task along this critical path is still ruled by its own skewed beta distribution. To establish the final probability for the entire project, we must sum these critical nodes together. According to the central limit theorem, the sum of many independent random variables approximates a perfect symmetrical normal distribution. To accurately model this bell curve, engineers calculate the project's total variance by summing the variances of only the activities sitting on the critical path. With the model built, we can finally compare the mathematical expected time against a real-world scheduled target date. We do this using the z-score equation, which calculates the exact probability of hitting the target date. The equation works by taking the scheduled target date, subtracting the expected path duration, and dividing it by the standard deviation of the project. By taking that resulting z-score and referencing a standard normal probability table, an engineer translates highly subjective task guesses into a hard, objective statistical percentage. Relying on rigid, deterministic, single-point time estimates creates fragile plans that shatter under the weight of real-world complexity. PERT solves this vulnerability by demanding 3-point estimates, locating the zero-slack critical path, and applying variance to build a probabilistic model. It replaces the amateur strategy of hoping a project finishes on time with the professional standard of mathematical verification. No methodology can completely eliminate uncertainty from a massive engineering project, but PERT does not exist to eliminate risk. It exists to make risk visible, calculable, and ultimately manageable.